more challenging to do. So you want to write these steps out kind of like this. These right here, to me, are harder for me to do in your head, and they're going to be harder for you to do in your head. So what I recommend you do, if you're evaluating a logarithm, and we're not doing this with a calculator, my suggestion is the first thing you ought to do is write that as log 1/3, 27, and just let it equal to some variable. I'm going to say x, okay? That's the best way to start that, okay? Now, we're going to write this in exponential form like we talked about last time. So when you do that, you'll have 1/3, remember that's the base, to that power x is equal to 27. So you want to get that written down. Now, these are the ones that are a little harder for you to do. So you're taking that base 1/3 to the x power equals 27, okay? All right, now what you want to do on this is you got to apply properties of exponents. Anytime you have a fraction to a power, that's the same as 1 to the x over 3 to the x, and then that's equal to 27. It's still hard to do in your head. You could do that if you really understand exponents, but these problems are designed so something happens, okay? If you think about 27, isn't 27 a power of 3? Yeah, so that's 3 to the third, right? What you'll do on these more difficult problems is they're usually designed so these are powers of the same base. So what I would recommend you do here is this, okay? I'm going to have you do this. Of course, 1 over x is 1. 1 to any power is 1. 3 to the x, and then write this as 3 to the third, okay, like that. Now, what you want to do, and this is what you always want to do on these problems, is kind of get down to this point. If you move the 3 to the x up, what happens to its exponent? Changes sign, right? Okay, anytime you move something across that fraction bar, the sign of that exponent changes, so you get to that point. Now, these problems that are more difficult, you always go about doing this way. And then the thing that you want to do, and you might want to write this down, the thing is this is how you conclude this. If the bases are the same, okay, then what do you have to conclude about the exponents? They have to be the same also. So if the bases are the same, that's the 3's, then what's going to end up happening is the exponents must be equal. Okay, that's what you do. So what you would do now is you would take these things and set them equal to each other to finish up the problem. So what you want to do is you would have negative x equals 3, divide both sides of that equation by -1, or do that in your head. So the answer of that problem would be -3, okay, like that. Now what I want to show you on this is I want you to understand why that's the answer to the problem. And when I do this next problem, we're going to do a lot of work. And the thing is, we're trying to make the bases the same, so the exponents are the same. Does that make sense? If the bases are the same, the exponents have to be the same. So you have to know your properties of exponents real good. Okay, over at the side, and you don't have to write this down, but you can if you want to. I would recommend it, because you can check your answer to every single one of these problems. So what we just found is the log base 1/3 of 27 equals -3. Let me show you how you can tell you're right. And if you take the time to do this a little bit, you'll understand and you'll learn your logarithms better. So we write that as 1/3 to the -3 equals 27. Okay, that's the key with logarithms, is writing from the log form to the exponential form. Okay, the other thing you got to know is if you have a fraction to a power, that means the numerator is to that power, and so is the denominator. Okay, so we're going to do that. Now, let me ask you this. This is important. How do you make those two negative exponents positive? You flip them, right? The 1 goes to the bottom, the -3 goes to the top, see? So what you would have then is 3 to the third over 1 to the third. So therefore, that's 27 over 1, so it's right. Okay? That's how you ultimately understand these logarithm problems, is by verifying your answer. Okay? You guys understand what I'm doing okay? All right, is everybody getting this down? Okay? All right? So the next one we're going to do basically the same way, and you want to start this off kind of like this. Okay? This one's pretty hard to do in your head, so write down log base 2 of 4 is equal to x. Do that. Okay. Now what you want to do is write it in exponential form. What's exponential form? Square root of 2 to the x power is equal to 4. So you want to start that way. Okay, square root of 2 to the x power is equal to 4. Now here's what you got to do. If you're going to get good with these problems, see like this one, see we got 3's the same. Okay, there's a 2. What would be a logical thing to do with the 4? Just like I did over here. 3's, what would you do? 2 to the second. Good. Okay. They're connected. They have to be. I've designed the problem so they are connected that way. So what you would have is you want to go ahead and change that to 2 to the second. And then you got to do this, okay? What is something you've learned to do with the square root of 2? What can you write it as in terms of an exponent? 1/2 power, right? Okay, remember a square root's a 1/2 power, so you want to take that thing and you want to write that as 2 to the 1/2 power, and then that whole thing is to the x power. Okay, and see where we're trying to go with this is ultimately we want 2 to a power equals 2 to a power. Okay, all right, so next thing is you got to know your exponent rules. All right, anytime you have a exponent and then another exponent, you multiply the exponents. We did a real quick review of this last time. For instance, if you had x to the second to the third, that's x to the 2 times 3, so that's x to the 6th. So what you do with this is you do 2 to the 1/2 times x is equal to 2 to the second. Okay, that's what we did, and that's the whole point of the problem, is we've accomplished the same thing we have over here. Now your bases are the same, right? So if the bases are the same, what's the deal with the exponents? They're the same also. Good. Okay, that's what you got to get down. And your ability to do this is going to depend on how well you know your exponent rules. So what you do is you just take the two exponents, set them equal to each other. So you'd have 1/2 x equals 2, and then you can solve that equation by multiplying both sides by 2. So you'd end up having on this problem, you would have x equals 4 would be the answer to that problem. Okay, now I'm going to check this one because it's real easy to check. And, you know, to me, one of the mistakes students make when they're learning math is they don't check stuff very good. And that's how you ultimately understand all this stuff, seriously. Okay, so here's how you would check. We're going to go back to the problem, log square root of 2 of 4 is equal to 4. Here's how you verify that it's right. What you do is you want to write this in exponential form. So write this as square root of 2 to the 4th power. And let's see if that isn't equal to 4. Okay? Okay, well it is, because what this is this is the square root of 2 to the 4th. That's another property of exponents. You can put that 4 under the radical. What is 2 to the 4th? What if you multiply 2 4 times? What do you get? 2, 4, 6, no, 2, 4, 6, 2, 4, 8, 16. Okay, so that's square root of 16. That's equal to 4. Okay, that's why it's right. So you want to understand that ability to check your answer on logarithms, and you'll get it down way better. Okay, you guys clear with what I'm doing? Okay, all right. Okay, so that kind of takes care of that. We're going to kind of now get into the graphing part of this. I've kind of given you the introduction. Now we're going to kind of get towards the graphing. The first thing we want to look at a little bit is we want to look at a domain of a logarithmic function. Okay. So one thing that's real important, and I'll explain why this is when you have a logarithm of any base, this thing right here must be a positive number. Okay, you can't do logarithms of negative numbers, and you can't do logarithms of 0, because it makes absolutely no sense to do that. Okay, so let me show you the y part on that. Okay, let's say that you had log base 10 of 10. Okay, do you know the answer to that? It's 1, right? Okay, because remember, if you did exactly what I just showed you, you would say 10 to the x equals 10. Well, x is 1, okay, because 10 to the first is equal to 10. So whenever you have a positive number, okay, you can reason that out. Okay, let's put a 0 here. Let's put log base 10 of 0. Okay, that is undefined. Let me explain why. If I set that equal to x, and if I wrote that in exponential form, I'd have 10 to the x equals 0. Okay, now let's see if you understand this. Can you think of any number that x could be that could make that 0? Okay, if you take 10 to any power, you get a positive number. Even if you do 10 to the 0 power, what's 10 to the 0 power? 1. What would be 10 to the negative 1? 1 over 10. Okay, so it's impossible. See, that doesn't have a solution. So this one right here has no solution. What if you had log base 10 of negative 10? Okay, what you would have is 10 to the x equals negative 10. Okay, can you think of any number that you would raise 10 to get a negative number? No, so that's what you got to understand. You got to understand how exponents work to understand logarithms. So the key thing on this is make a loud note to yourself somehow that you can only take logs of positive numbers, okay? Zeros unacceptable, negatives are unacceptable. So what that means you're going to do when you're finding all of these domains on this page, what you need to do is focus just on what we call the argument. That's what you're taking the log of. So what you would do in this problem, this one's real simple. Take that, and what does it have to be greater than? 0. There you go. Now that's a simple inequality to solve. So you solve that inequality. You can subtract 2 from both sides. So you'd have x is greater than negative 2. So you can write your domain in one of two ways. You could do the set builder like I've taught you, set of x such that x is greater than negative 2. How would that go in interval notation? Negative 2, comma, infinity. Thank you. Very good. Okay, so we got that. All right, so that one's a real simple one. Sometimes they're that simple. So x has to be some number bigger than negative 2. Okay, you do the next one the same way. It doesn't matter what the base is. You want to look at that, and you want to take this and set that strictly greater than 0. Okay, now we have learned how to do inequalities. That's what we were working on. The last class is how to do what we call rational inequalities, okay? Now, you don't just try to get x by itself on this because that's a rational inequality. What you have to do is you have to do this sign chart thing, okay? You have to, okay? Because you can't isolate x by itself like you can on problem 1, okay? So let me ask you a question on this. What is the vertical asymptote on 1 over x plus 4? Negative 4. You're undefined at negative 4, right? So what we worked on last class, as I said, okay, at x equals negative 4, you have a vertical asymptote. I was kind of showing you to do that like that, right? Then what do? Test points. Remember we did the test points and we did that sign chart. So what we do now is we pick test points. So if you pick something out here, a number smaller than negative 4, that would be negative 5. Plug it into your function. You'd have 1 over negative 5 plus 4. So that's 1 over negative 1. So that's a negative number. Okay, so that would not be the solution because what are we doing? We're trying to figure out where this thing is bigger than 0. We just figured out where it's not bigger than 0. Okay, so let's go over here and let's see what we get. Okay, test point bigger than negative 4 could be 0 if you want. It doesn't matter. As long as it's bigger than negative 4, it'll work. So you'd have 1 over 0 plus 4. What kind of number is that, positive or negative? Positive, okay? So that is your answer to your problem because of that. So what you found is where this expression is positive is bigger than negative 4. So what you would say is set of x such that x is strictly greater than negative 4, or you could say negative 4 to infinity if you did that in interval notation, okay? So see what I'm doing on every single one of these problems is you're going to start by taking the argument greater than 0, and then you got to know how to solve these different inequalities. Okay, there's different techniques for different ones. Okay, all right, let's take a look at this one. This one you got to really pay attention to one little detail on this. So again, the argument is x plus 1 squared. You're going to set that greater than 0. Now that's exactly the same kind of thing we were working on earlier this week, like really from section 2.7. Okay. So if you solved this equation, you can do this in your head. Okay, what value of x would cause that to be 0 in your head? Negative 1, right. Okay, so what you're going to do is you're going to do a sign chart, same way. Again, because this is what we call a polynomial inequality. You can't just isolate x like you can on number 1. So what we'll do here is we'll just put x equals negative 1, and then we're going to do test points. Okay. Now what will happen on this one is if you take a number like negative 2 and plug it in, you would have negative 2 plus 1 squared. In your head, is that positive or negative? That's positive, isn't it? Right? Okay, so you're getting a positive because you're squaring negative 1, correct? Okay, take a test point bigger than negative 1, like 0, Plug that in, 0 plus 1 squared, what is that? It's positive also, okay? So what you do on this, you've got to be real careful about one detail on this problem. So we're trying to figure out where this is positive. It looks like everywhere. Everywhere is not the answer. The domain would not be all real numbers. Do you know why? Yeah, when you're at -1, you're not positive. You're 0, right? So you got to make sure that you pay attention to that little detail of that. So, yeah, right here you're 0. So really what you would have graphically is you'd have like a bubble go that way and go that way. Okay, so you would write your domain like this. You could say set of x is not equal to -1, or in interval notation you could say -infinity to -1 union -1 to infinity. So it's everywhere except that one point, okay? And another way to look at this problem is if you square something, it's positive, right? So it's going to be everywhere except what makes that 0. Okay, does that make sense? That's a good clue to look at in the problem is you got something square, okay? Okay, let's look at this next one. Again, same idea. You want to start by taking the argument and you want to set that greater than 0. Okay, now again, the thing that you want to make sure that you do is, except for problem number 1, you have to do sign charts. You have to, okay? You can't just get x by itself and take a cube root. You can't do that. You got to analyze the signs. So what I'm going to do with this is we're going to go ahead and we're going to solve this equation first of all. So I have x cubed minus 1 is equal to 0, like that. Okay, now this one you can move the 1 to the other side, so it's x cubed equals 1. Then you can cube root both sides, so you get x equals 1. Now you can do that in your head also. 1 to the third minus 1 is equal to 0. So what you would want to do with this problem then is you'd want to do this. Okay, you would want to look at a number line where x is equal to positive 1 like that then. Okay, so then what we would want to do from there is exactly the same kind of thing. Just pick test points and plug it into x cubed minus 1. So I'm going to take like 0 there. So that would be 0 cubed minus 1. What is that, negative or positive? That's negative, so that's not the answer, right? We're looking for where it's positive. Take a test point out here, take 2. Then you'd have 2 cubed minus 1. That's a positive, so that's where your answer exists, see. Okay, so what would happen on this then is the answer to the problem would be over here. So we would say I can't talk. What am I trying to say? Set builder notation, we'd say set of x, and then we'd say x is greater than 1. In interval notation, we'd say 1 infinity, like that, okay? All right, do you guys understand what I just did? Okay, do you understand why I'm doing sign charts? Because a lot of times when I see students do this, they forget all about that. Okay, the only one that you can do with a basic inequality is number 1. Okay, there's a real easy way to tell you're right on your calculator. So I want you to just watch this. Like on the last problem, I'm going to put in ln of x to the third minus 1 and just graph that. And let's graph that in a standard window and let's see what it looks like. Okay, well, notice my graph starts at 1 and goes to the right. Okay, so visually you can tell the domain is 1 to infinity, see? So you can always look at these things on your graphing calculator to get a good idea of whether you're on the right track. Okay, so when you're doing graphing, that's a real important thing. You'll see logarithms all over the place in calculus, particularly if you get up a little higher than like Calc 2. There's a lot of that in there. All right, the next thing I want to look at is how you graph a logarithm. I have a certain way that I teach it that I think is a pretty simple way to learn how to do this. And what I like to have students do is when you graph a logarithm is to graph the inverse. Okay, one thing that you want to make sure that you understand is log base 10 of x, and if you have y equals that, if you have y equals 10 to the x, those things are what we call inverses. Okay, that's something we talked about a little bit last time. So what we're going to do, on this is we're going to graph this thing first. Okay, and if you can do this, it makes graphing the logarithm super easy. Okay, so we're just going to fill out this table of values for y equals 10 to the x. Okay, so let's start here. 10 to the 0, what's that? 1. 10 to the first, what's that? 10. 10 to the second, 100. Okay, we did a lot of this kind of stuff in Tuesday's class. Now 10 to the negative 1, what's that? 1 over 10. Okay, remember you make the exponent positive, so that's 1 over 10. And 10 to the negative 2, that is 1 over 10 squared. So that's 1 over 100 like that. Okay, so that's how you do that. And then we're going to draw that function. Go ahead and do that now. Okay, so we're just going to put the ones that fit on here. So what you're going to have, let's start with the point 0, 1. That's your y-intercept. Then you got the point 1, 10. Okay, and remember we talked about this last time. If you were to graph negative 1, 1/10 and negative 2, 1, 100th, all that's going to happen out here is that thing is just going to get closer and closer to the x-axis. You have a horizontal asymptote, and then this thing is going to go up like that, and it's going to go to infinity. Okay, it's going to keep growing forever. So this right here would be the graph of y equals 10 to the x. Okay, all right, everybody with me there? Okay. Now, let me see if you know this from your background. How do you find an inverse? What happens to the points on inverses? They switch. They go backwards, okay? So actually, when you make this table of values, all I'm doing is doing this backwards. So see that you have this point 110. Well, what we're going to end up doing on this is that's just going to become this. So that point is going to become 10, 1. Okay? What I'm doing is just flipping the points. Okay, you have the point 2, 100. That's going to change to the point 102. Okay, I've got the point 0, 1. That's going to change into the point 1, 0. Okay, I don't know why I put a 2 there. I don't need that. Okay, now point 1 is 1/10. So if I went through and switched these points here, then you would have the point 1/10, negative 1 like that. Okay, 1 over 100 is 0.001. So again, I'm going to flip the points like that. So this is 1 over 100. This thing is going to flip to negative 2. So what I want to show you on this is all of these points just go backwards. If you're going to graph the logarithm, you graph all of those points backwards. Okay? So let us do that. Okay? So I'll highlight the ones we're going to do. Let's do 10, 1. Okay? That's the inverse of that. Let's do 1, 0. That's good enough, okay? And then the rest of them, I'll show you what happens. So if I graph the point 1, 0, that's going to be here. If I graph the point 10, 1, that's over like that. And then if I graph like these points, like 1/10, negative 1, well, all that means, if you're graphing 1/10, negative 1, it just means you're barely over and you're down 1, right? So what's going to happen is if you plotted that point and just sort of estimate it, the graph of the logarithm is going to go like this. Okay, so that would be how that graph goes. So the easiest way to learn how to graph a logarithm is to know how to graph the inverse, because it's easier. And then once you do that, flip all your points backwards. That's the way I'm going to show you. Does that make any sense to you? Okay. Now the other thing that's worth knowing on this, for an inverse, if you were to graph y equals x, that's how they're symmetrical. So y equals x is a line that goes through the origin that's at a 45-degree angle. You don't have to get that perfectly accurate, but it is nice if you write on your paper that you know that that is symmetrical about that line then. Okay, so that would be how you graph the natural logarithm of 10 to the x. Okay, if you're going to take calculus, I deal with this all the time when I teach calculus, when you're working with limits and derivatives and stuff like that, you need to have a quick picture of how graphs of functions go. That's why we spend so much time in this class in college algebra on functions, because that's what you deal with in calculus, okay? All right, does anybody have a question about what I just did? Okay, are we all solid? Okay, so you want to make sure that you know that exponentials and logarithms are inverses of each other. Okay, let's go to the next page. I'm going to do the same thing for e to the x. So we're going to graph, ultimately our goal is to graph ln of x. Okay, so this again is just log base e of x. That's the natural logarithm. We talked about that on Tuesday's class. So what we're going to do is these are inverses of each other. Okay, so we're going to graph e to the x first of all. So let's start with filling out this table of values. So let's start with 0. So that would be e to the first, or no, e to the 0. So that would be equal to 1. Okay, then we're going to go e to the first. Well, I'm just going to have you put e there. What is e close to? If you rounded it, what is it about? 2.7. You want to know that. Okay, it's kind of like pi is 3.14, e is around 2.7. Okay, now we go e to the second, so just put e to the second there. And if you took your calculator, you would get 7.4. Okay, I don't expect you to know that. You want to know that e is about 2.7. Okay, if you go to the next one, e to the negative 1, that would just be 1 over e to the first. And then finally, e to the negative 2 is going to be 1 over e squared like that. Okay, so what we're going to do is we're going to plot those points, and then we'll work on the logarithm like that. Okay, all right, let's plot them all. We got 0, 1, so we got a point there. Then I've got, this one would be over 1, up about 2.7, and then over 2, and up about 7.4. Okay, the graph of e to the x is going to go like that, and then it's just going to basically level off like that. So let's label that as y equals e to the x. Okay, like that. Okay? All right. Now, before I go into this logarithm, let's do this because this is pretty important on this. What would be the domain of this function we just graphed? The domain, what is x? X could be anything, right? What is the range? 0 to infinity, right? So the range is y, and you want to write those down.
Would it be 0 as a parentheses?
Yeah, 0 is going to be in a parenthesis. It has to be, because you never hit the x-axis.
Even though it's in the right.
Yeah, okay, you'll never do that, because the idea is, see, what you're going to do is you're just going to end up with 1 over a bigger and bigger and bigger number. Okay, and that's always going to go to 0. Okay, so the domain is all real numbers. Okay, and the range is going to be 0 to infinity. So, okay, so that takes care of that first graph. Okay, now what you want to do is you want to flip around these points, okay, like this. All right, so do this. Take this and write this one as 1 over e squared, negative 2, 1 over e, negative 1, 1, 0, e, 1, and then e squared and 2 like that. So again, if you're going to graph the logarithm, flip the points because you know what the inverse is, and then plot them, okay? All right, so let's go ahead and do that. Let's do like 1, 0. That's kind of the only basic point. This point right here is like about 2.71. So go over about 2.7 and up 1. This point, e squared, is like about 7.4. So if you were to go over around 7.4 up 2, that would give you kind of a good point like that. Then just sketch it. What's going to happen is that's going to go like that, and then it's going to approach the y-axis like that. So what happens on an inverse is this horizontal asymptote changes into a vertical asymptote. Everything goes backwards. Does that make sense? Okay. Now, what we will do from here is, what does it look like the domain of the green graph is? 0 to infinity, right? What does it look like the range of the green graph is? Everything. It goes infinitely low, gets infinitely high. Okay, what happens is this. So this is what I want you to know, is what turns out on this, what happens is the domain of the function turns out to be the range of the inverse. Everything's backwards. Domain turns into range. Okay, the range of the function turns out to be the domain. Okay, you can tell by looking at the green graph, that's right, yeah.
If you did a composition of functions on that, like f of g of x, wouldn't that still equal x with these two because they're inverse?
Yes, exactly, they are. So if you did a composition, if you did this, and actually this is sort of a good thing to do because it's real easy. We'll see if you guys catch this or not. If I did f composed of g of x, okay, f would be e to the x, and then if I plug g in, I'd have e to the ln x. Do you guys know what that is? I taught you that Tuesday. It's x, okay? That's a property of exponents, so good observation. Remember, the property I showed you was b to the log base b of x equals x. So that's basically comes from that property. So that's how you prove that they're inverses, if you do exactly what you said. Okay? All right? Okay, any questions there? Okay, all right. So we want to be solid with these graphs. We're going to do a little bit with logarithms in transformations, but not a lot. So first thing I'm going to do with this one is we're going to find the inverse and graph it. Okay? So we're going to be, ultimately we're going to graph this. So go ahead and write down y equals ln of x minus 3. Okay? Now you want to make sure you know how to crunch out inverses. It's real important. Okay, what do you do with x and y when you find an inverse? You flip them. Okay, so the first thing you want to do is change the y to x, and then you want to change the x to a y. Okay, so you got to do that. Now you've got to solve this equation for y in order to get this inverse. Okay, so what I'm going to do is you want to know that the ln is a log base e of y minus 3 like that. Okay, now you're going to write that in exponential form. So what do I mean if I say write this in exponential form? What would it be? E to what power? X power equals y minus 3. So we would say e to the x is equal to y minus 3. Okay, if you're going to solve for y, you've got to know how to change that logarithm to an exponential form. Okay, now add 3 to both sides. You can do that in your head. Just move the 3 so you would have y equals e to the x plus 3 like this. Okay, so what you would get is f inverse would just be e to the x plus 3 like that. Okay, so that's what we're going to end up getting. Okay, now to me, the best way to learn how to graph logarithms is to graph that instead, and then switch all the points. Okay, so what that is, if you're doing e to the x plus 3, we've already done the graph of e, so let me show you what would be a reasonable way to do this. Is let's just make a quick table of values for e to the x because we already did. Yeah, go ahead.
Why do you put the 3 exponent?
I don't know. I didn't mean to. I think I didn't bring that down enough. So that should be e to the x plus 3 like this. Thank you. Yeah, I didn't write it in a good way. So that would be e to the x plus 3. Okay? All right. So let's go ahead and make our table. -2, -1, 0, 1, 2. We've already done this. I'm going to do this super fast. E to the 0 is 1. E to the first is just e, which is about 2.7. E to the second, we'll write that as e to the second. So that's about 7.4. Okay, these things, this would be 1 over e, and that would be 1 over e squared. Okay, so here's what I want to see if you're catching on to or not. Okay, so we know how to graph e. We just plot those points. Well, what would be the graph of e to the x plus 3? What is that plus 3 going to do to that graph? It's going to move everything up 3. Good. Okay. So what you want to do on this then is we're just going to, in our mind, let's just start by plotting these points here. And you don't have to plot them all. We got like 0, 1. Then we got 1, 2.7. And then we have over 2 up about 7.4 like that. I'll just really, really super lightly dash that in. Okay, then we're going to do like a stage where we just bring that whole thing up 3. Everything goes up 3. So what you would find on this is this point 0, 1, that would just go 1, 2, 3 up, so that's now up 4. This point here just go 1, 2, 3 up, and so forth. Just kind of estimate. It doesn't have to be perfect. So we would end up having a graph that looks like that, and then it would level off not at the x-axis, it'd level off at y equals 3. Does that make sense why it would level off at y equals 3? Because originally it levels off at the x-axis, so that's how that goes, okay? All right? So we have that. Now what we're going to do is we're just going to flip all these points backwards. So I'm just going to kind of write the key points here. So what's going to happen is after you get these points, you just flip them all backwards. So the key point on here to me is this point right here. That's a point 0, 4. So that's going to turn into the point 4, 0, like that. Okay, that's the key point. The rest of them you could estimate. This point right here, when I'm talking about on the green graph, that is basically the point 1, and then 2.7 plus 3 would be, that one was like about 5.7. Okay, where I'm getting that is I'm just moving all these points up by 3 because of that transformation. So this one, do it backwards. You would go over about 5.7, and then you would go up 1, about like that. And what you'd end up having is you'd have a graph that goes like that, and then it would go like kind of towards a vertical asymptote like this, okay? So what I'm trying to show you on this, you got to keep track of this with the number crunching, is do e to the x first. Okay, that's the one in red. Then what do? We move it up 3, right? And then everything goes backwards. Just get a couple of points, that's usually significant. And I want you to understand this. What happened to the horizontal asymptote? It turned into what? Vertical asymptotes. Everything's backwards, see? Okay, so that really turned into that. Okay, and everything else stays the same, all right? So what you would have with this then is with your domain and range, let's take a look at the function, okay? The function that we have to start with, let's do this function right here. This is the logarithm function. Okay, look at the graph I highlighted in blue. What does it look like its domain is? Where to where? 3 to infinity, good. Okay, that's clearly 3 to infinity. How about the range of the blue graph, the inverse? What does that look like? Everything, right. Okay, so that's all real numbers. Okay, so what I want you to know, and this is important, is if you do the domain of your function, that will turn into the range of your inverse. Whoops, why am I writing that? It's the same thing. So what this would be is this would be 3 infinity. Okay, look at the yellow graph. Does the range of the yellow graph look like it's going 3 to infinity? What do you think? Range of the yellow graph, 3 to infinity? Okay, yeah, okay. And then the range of the function turns into the domain of the inverse. How about the yellow graph? Does its domain look like all real numbers? Okay, because that's an important thing you want to know is since you're doing inverses, these things flip-flop. The domain of one becomes the range of the other and vice versa. All right, is that logical? Tell me. I can't tell. It's logical to you. How about the other people? Okay, you got a question?
So for step 2, or next to 2, where you log base e, how does that then translate and eliminate, how does that get e? So you put e in there to natural log, and that gives you log base e, which is natural log.
Yeah, well, okay, what I'm doing here is I'm solving for y. So I interchange the variables. That's step 1, right? Okay, and then what I did is I write the ln of log base e, because now you're doing exponential form. Exponential form says you take the base e to that power equal to this expression y minus 3. So I'm doing is I'm writing this as e to the x equals y minus 3. Then I'm solving for y, so I'm adding 3 to both sides. I didn't write that real well. So it's e to the x plus 3.
Yeah.
That's your inverse. Okay, flip the variables, solve the equation for y.
I just got tripped up on the solving part.
Okay, all right, very good. Okay, any other question about that? Okay, all right. Okay, so I'm going to run through a couple of more graphs, then we'll do some equations. This sometimes is a real problem area for students in college algebra. So you're really wanting to make the connection of the logarithm and exponential being inverses of each other, okay? So I'll do a couple more of these, a little bit of repetition here, okay? Okay, so what we're going to do is we're going to take this and we're going to find its inverse. Go ahead and write it down, please. Everyone, please. Okay, so what do I do if I do an inverse? First thing I do is flip the variables. That's step 1. Okay, go ahead and do that. You have x equals logarithm base 3 of y. This is what I could tell some of you weren't catching on to on the previous problem. Now what? Solve for y. Exactly. You got to figure out what y is. How do you solve for y on this? Exponential form, right? So you would say 3 to the x is equal to y. Okay, so what you get then is your inverse. F inverse of x is equal to 3 to the x power. Okay, now see if you're going to graph log base 3 of x, you want to graph that first because it's easier. Then you flip all the points. Okay, it's a lot easier because what happens to students is they try to make a table of values on log base 3 of x and they don't know what to do without their calculator. So it's a little easier to do it this way, see. All right, is everybody okay with how I got the inverse? Okay, now that's one that you want to know, by the way. So like if you have log base 5 of x, what's its inverse? X to the 5th, okay, like that. So you're basically just flipping the variables. Whoops, hold on, I wrote that wrong, 5 to the x. So it would be that, okay? All right, so let's go ahead and let's do the chart on 3 to the x, okay? That's our inverse. So let's just use -2, -1, 0, 1, 2. That's always a good bet if you're doing an exponential equation, okay? Crunch it out. So let's see, we'd have 3 to the 0 is 1, 3 to the first is 3, 3 to the second is 9. That takes care of that. Then you would have 3 to the -1. What's 3 to the -1? 1 over 3. Just leave it that way. Don't get decimals. 3 to the -2. What's that? 1 over 3 to the second, so it's 1 over 9. Okay, like that. Okay, well, let's go ahead and plot it. Okay, get that out of the way. And you're going to find these exponential functions are going to start looking the same thing over and over again. So we've got the 0.01, the 0.13, and the 0.29. And then everything else is just going to kind of level off at the x-axis. That's how your basic exponential function goes, is like that. Okay? All right, so with this one then, what are you going to do on the log? You're just going to flip the points. So what you do is you just do this. Okay, that would be 9, 2. This would change to 3, 1. That would change to 1, 0. And then 1/3 -1. And 1 over 9 -2 like that. Okay, so that's how your points change. Plot them and you'll have your graph of your logarithm. Okay, it's way easier to do that problem this way. Okay, so I'll just plot these points. I got 9, 2, 3, 1. And 1, 0, and then the rest of them are just real between 0 and 1, so the graph of your logarithm goes like that. Okay, that's what it looks like. So that would be the graph of y equals log base 3 of x like that. All right, so what happens on this is what you really want to do is you want to get that inverse done and then just turn everything around and you got it. To me, that's the easiest way to teach a student how to do a graph of a logarithm. Okay. Everybody with me there? Okay, now see, doing the graph of y equals 3 to the x is arithmetic. That's doing arithmetic and plotting points, okay? All right, so let's look at this then, the domain of f of x. F of x is the logarithm. So here is the logarithm, the yellow graph. What is the domain of the yellow graph? 0 to infinity, good. What's the range of the yellow graph? All real numbers, -infinity to infinity, okay? So here's what happens. What happens to the domain of the original function? It turns into the range of the inverse. So you just automatically write those down. The range of f of x, what does that turn into? The domain of the inverse. Okay, the inverse is the one that's in blue. Does that match to you? The range of this function, does that look like 0 to infinity? Okay, how about the domain of that function? Does that look like all real numbers? Okay, you want to make that connection. Okay, everything goes backwards. X and Y are backwards when you have an inverse. That's why domain and range flip also. Okay, future test question. That's like beautiful test question in the future. Okay, because it really shows that students understand that connection between logarithms and inverses. Okay, I always ask that same kind of thing in college algebra. Okay. All right, we're going to do one more graph, and just one with transformations. In your homework, you're not going to do a lot of complicated transformations on a logarithm. You basically want to get the idea of how that works, and then get a rough idea of how that graph's going to work out. So we're going to do this last problem basically the same way, but we're going to do transformations first of all. This problem's all about transformations. So what we're going to end up doing with this one is ultimately we're graphing f of x equals 2 plus log base 2 of x. Okay, the way I'm going to show you how to do this is forget about the transformations of 2 for a minute and just focus on this part right here. So if you have y is equal to log base 2 of x, can you tell me in your head what the inverse is? That's important.
2x.
It's 2 to the x, right? Okay, just like the last problem, you had log base 3 of x and you had 3 to the x. You don't have to go through the details of that if you don't want to, but if you did, what would happen is if you did the inverse of this logarithm, you would have x equals log base 2 of y. Then if you write that in exponential form, you have 2 to the x equals y. Okay, so you can do that inverse real easily on that problem. Okay, so what we're going to do, and we've done this already, like 2 or 3 times already, we're going to do the graph of this. Okay, that's the inverse. We're not going to worry about the transformations till the very end. So we're going to do this real quickly. Just use these same old points right here. And you want to just do this boom, boom. Just rock right through that. Okay, so you've got 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the negative 1 is a half, and 2 to the negative 2 is 1/4 like that. Okay, now we're not going to graph that or anything. Now, tell me how you're going to make the table of values for log base 2 of x. You're going to flip them good. Okay, all right? So what we have on, you didn't even get what I was saying, did you? You kind of did? Okay, all right. It's a Devo thing, like from 80s, the group Devo in the beginning of the NTV world. Okay, so let's go ahead and let's flip all these things. Okay, like that, and then we're going to plot that. Okay, don't worry about plotting the 2 to the x, because all that is a tool to get these key points like this. Okay, so let's plot this. We've got the point 1, 0, then we've got the point 2, 1, and the point 4, 2, and I'll zoom on this a little bit bigger so you can see that a little bit better. I just plot those out. These are the 3 key points to me on that. So I'm just going to kind of do a dashed line there and represent that that's y equals 2 to the x. And then we're going to go down to the y-axis like that. Okay? All right, so what we're going to do with this is, now we're going to do the transformation. So what we're going to do next here is we're going to do f of x equals 2 plus 2 log base 2 of x. Okay, that's got transformations to it. So let me see if you know what these transformations are or not. Okay, what does that plus do that's outside of the logarithm? Takes you up 2, good. What does this one do? That multiplies y's by 2, so what does it do? Causes everything to stretch. The y's get bigger, therefore it stretches this way, okay? So here's what you're basically going to do on this problem. All you really want to look at is these 3 points that we have. The 3 points that we graphed that were important were 4, 2, 2, 1, 1, 0. So what you're going to do with this then is, first of all, you want to stretch the y. So you just do 2 times 0, and then you bring up the 2 like that. Okay, so that's going to give you a new point equals 2. Okay, that's how that works out. Then the next one, 2, 1, you want to stretch the y. Double the y value of 1. Bring it up 2 by adding. Turn this into an arithmetic problem, and you'll do better. Okay, same thing here. Double the y. Bring it up 2. So that would be 2 plus 2. Whoops, hold on. Did I just say 2 plus, oh, never mind. 2 plus 4 is 6, right? So we got that. I thought I made a mistake, but I didn't. Okay, so basically what you do is just plot those points, and that will give you the final graph on that. So again, you're multiplying y by 2, and then moving it up 2. That's how the transformations go. So just plot these points, and then we should have what the final product looks like. So we still got the point 1, 0, hold on, that's 1, 2. That changed to 1, 2. This point changed to 2, 4. And then that point changed to 4, 6. Okay, so plot those points. So you go over 1 up 2, over 2 up 4, and then finally over 4 up 6, and then your graph would look like that. Okay, now that would still approach the y-axis, but you can tell how it's stretched, right? And you can pretty well tell that everything got moved up after that stretch. Okay, the point that's the easiest to see that moved up 2 is this point. They all did move up 2, but they did that after the stretch part. So what happens, think of this, that is a y value of 2. If you double that by that factor of 2, that goes to 4, then it moves up 2. Does that make any sense? You've got to do the stretching first, then up 2. Same thing here, stretch to there, up 2. If you can do that, then you understand what's going on in the problem. Okay? Yes?
The red graph, Isn't it log 2 of x?
No, what I ended up doing on that one is, oh yes, thank you. We switched the points. Yeah, we started by doing y equals 2 to the x, then we switched the points to do that. Thank you. So that's what that is. And then this one would be, the green one is y equals 2 plus 2 log base 2x like that. Okay? So that's it. That's how you would end up putting that together to get that final product. Is everybody with me on that? Okay? So what I'm trying to get you to do is to do logarithms, do the exponential, then flip the points because of the inverse, and then do the transformations. Okay? All right, so I'm not going to do the inverse on that. I mainly wanted to do the graph. Okay? All right, let's go ahead and let's do our break, and when we come back, we'll work, finish this up, and then we'll start on again here. So if you're going to put this in, you have to go like this. You have to go to the math button, write it down if you need to. A lot of times forget where this is, so you want to get to math, and then you want to go all the way down, and on an 84, you should find it down where it says A. There will be 9 options, and then there will be a few more. So it's this one that says log base like that. So what you do is you press enter, and then you just put it in. Okay, so it's going to have the subscript of 2, and then you would have the x like that. So that's how you graph log base 2 of x on your calculator. Okay, if you have an 84 or higher, 83, sorry, you're out of luck. They didn't put that in until the 84. Okay, the rest of it's pretty straightforward. You do 2 to the x, okay, like that. And then y equals x. This is just kind of the basic overview of what I want you to see is how that goes. So now if you've got everything in, just go zoom 6 for a standard window. And this is what I've been showing you tonight so far. So the blue graph is the logarithm. The red graph is the exponential. Y equals x is how they are symmetrical because they're inverses. Okay? All right, everybody find that button. Okay, everybody with me? Okay? You got to have an 84 or higher to find that. You can do without it. I'll show you how you can do without that a little bit later. Okay, so let's go ahead and let's finish up this last page. And we're going to do some logarithmic equations to kind of finish this up. Now, you're solving equations that have logs in it. So really what you always try to do is you try to write in exponential form. The ones in this section are pretty basic, straightforward examples. Okay, so if we do this, if we write this in exponential form, we're going to end up having what? 2 to the third is equal to 2x plus 1. Okay, solve that equation. That's going to be a super easy equation for you to solve. So that's 8 equals 2x plus 1. Okay, then you could subtract 1 from both sides, or you can just move the 1 to the other side. So you'd end up having 7 equals 2x. Then if you divide both sides by 2, the answer to that problem is x equals 7/2. Okay, when you have an equation with a logarithm in it, you got to try to write it in exponential form. Now, we're not going to do the more complicated ones, I think, until the next section. We just want to start off with the basics. Okay, if you do this one, exponential form, how does that go? X to the third power is equal to 1 over 8. Okay, how do you solve an equation if it's x to the third equals something? What do you do to both sides? Cube root, right. Okay, just like you do a square root if it was x squared. What you want to do on this is you want to do a cube root of both sides. So that would be x. What's the cube root of 1? 1. What's the cube root of 8? 2, because 2 times 2 times 2 3 times is equal to 8. So the answer to that problem is 1/2. Okay, so once you get that in exponential form, you should encounter an equation we've learned how to solve this semester, okay? All right, this last one here, you're going to say 5 to the second is equal to x squared plus x plus 4. So that's going to give 25 equals x squared plus x plus 4 like that. What kind of equation is that? It's quadratic. Okay, so what do you need to do? One side equals 0. Good. Okay, so we're going to do that. So just move the 25 to the other side. So you'll have x squared plus x plus 4 minus 25. Okay, so that'll give 0 equals x squared plus x minus 21, I think, if I'm doing that right. Okay, so then what you'd have to do on this is you would have to solve this with quadratic formula because it doesn't factor. Okay, yeah, well, that's a bummer, but we can do it. Okay, so and I want to finish the problem because there's something you have to really pay attention to on some of these problems. So this one you just want to go to the quadratic formula. So I've got everything written out fine. So we just say negative b is 1, then plus or minus the square root of b squared, 1 squared, and then 4ac, a is 1, c is negative 21, then all over 2a like that. Okay, and we'll just simplify and we'll have the answer. So that's negative 1 plus or minus the square root of 1 plus, you got two negatives there, so plus 84 over 2. So you'd have negative 2 plus or minus square root of 85 over 2. Now that's a quadratic equation, so you have to follow the process on that. Okay? All right, is everybody okay with what I did there?
Why is it negative 2 plus or minus?
I have no idea. Okay, what should that be? I do stuff like that sometimes. I have no idea why. I think sometimes I can't talk and write at the same time or something. All right, so anyway, everybody got that okay? All right, now I'm not going to do anything with the checking on this one. I want to just give you the idea of what you do to solve a logarithmic equation, okay? All right, everybody with me on what I just did? Okay, then once you get an exponential form, you're now just kind of looking at your